Morning. Morning, everyone. Come on in. How's everybody doing? Questions while we wait? How are we doing with the material? Should be coming out in the next few days. Everything's been marked. Everything's been marked. We're just trying to figure out what to do with the late submissions. Go ahead, Niloy. Yeah, we're just trying to figure out what to do with late submissions and this and that. But yeah, so in the next few days, today, tomorrow, it's coming. Questions while Niloy is, oh, there it is. Two different values for Lagrange multipliers. What do you mean by that? Do you mean two different values for the lambda? Or do you mean two different points using Lagrange multipliers? Well, if you get two different values for the lambda, you just investigate what happens. You just investigate what happens with both of these values. Gabriella, the midterm grades are coming soon. This week for sure. Well, I mean, of course, you right. Right. So, I mean, let's look at that. 2x equals lambda 2x, and 2y equals minus lambda 2y. Right. So let's discuss that. I actually haven't looked at the average yet, Cam. Let's discuss that. So from the first one, bring the 2x to the other side, and you get 2x minus lambda 2x is equal to 0. So if you factor out a 2x, you get this. So two things happen here. Either x is equal to 0 or lambda is equal to 1. And from here, you'll get that y is equal to 0 or lambda is equal to minus 1. So, is it blurry? You know, I cleaned the camera. Does anybody else feel that it's blurry? Not as crisp as it used to be? Okay, thanks. So we have these things, right? So, you know, if you start with this, you have two possibilities. So y equals 0 or this. So, you know, you start by investigating the first one. And y equals 0, then you have these two things. So y equals 0 and x equals 0. That gives you a point, the origin. Or y equals 0 and lambda is equal to 1. And then you investigate what happens there. Or lambda is equal to -1 combined with x equal to 0. And you see what comes out of that. Or lambda is equal to -1 and lambda is equal to 1. Well, you know that's not possible. So that's not going to be a possibility. That's not going to give you anything. So there it is. Right, Fotini, because this is really two ways to view it. So Fotini is asking, why is lambda f minus, gradient of f minus gradient of g equal to 0, the same as gradient of f plus lambda gradient of g is equal to 0. And that's because right? I mean, lambda is some unknown constant. So if you replace lambda by negative mu, then this becomes gradient of f plus mu gradient of g is equal to 0. So whatever happens, it's going to be the negative of the other. Exactly that. So as back to Naloy, we investigate each case one by one. He's feeling that it's not very efficient. Possibly. I don't know that there's a more efficient approach, but in any case, you don't have a ton of cases. So it's not a big deal. Questions? Somebody wants to see Lagrange multipliers with two constraints. Let's go back to the Lagrange multipliers with two constraints that I actually discussed last time. And let me remind you what the question was. And, ironically, well, again, Naloy is suggesting that there could be a more efficient way. Lambda probably shouldn't be taking on different values. And, in fact, in a lot of questions, I try to stay away from actually solving for lambda. Right? It's going to be very, very rare that I actually solve for lambda. So it's not a big deal. And like I said, you probably shouldn't worry too much about being inefficient here, because there's usually very little to do anyways. I mean, the solving of the equations is the most time-consuming part. If you're left with a few cases, that's usually very easy to deal with. And maybe that's where the inefficiency comes from. Instead of pinpointing what could be put aside, you just deal with all the cases because that's going to be fastest. Yeah, that's not a bad answer. It's going to be faster to deal with all the cases than to try to discard some. Let's go back to this question, which we did last time. And the irony is that I had suggested that you should be questioning the questions themselves, asking yourself if there is a max, if there is a min. We had solved this, and I had suggested we had an absolute max and an absolute min. And we hadn't, and we left it as that. Thankfully, Kai Wen, and I hope I'm pronouncing your name correctly, went back to this and gave it some thought and noticed that if you take a large value of X and an almost as large value of Y, it's going to satisfy this. And for a large value of Y, if you subtract an almost as large value of Z, then it's going to satisfy that as well. Meaning that you have as large values of X, Y, and Z as you want. And it's clear that there is no maximum here. Marie, are we talking about this one here? What I'm suggesting is some books have different approaches, right? Some books, I mean, in our case, our book suggests that you want the gradients to be multiples of each other, or equivalently, this part right here. Some books define a Lagrange operator as f plus lambda g. And you want critical points of this Lagrange operator, which gives you essentially this. So, I mean, they're different. One is minus, the other is plus. But of course, you recognize that if you make a simple change of variables, lambda is minus mu, then this one becomes that one, right? So it's the same. It's really the same, right? Whatever value you get for lambda here, it's going to be the negative value that you get here. And that's it. So different books have different approaches. They are equivalent. So what I'm suggesting, and what Kai Wen pointed out, is that there is no maximum here. There is no maximum because, in fact, the intersection here is not bounded, right? What is this? You know what that is. This is the equation of a plane in 3D. Here, y squared is equal to 1 plus z squared. Right? I mean, first of all, there is no x specified. So you can graph that in the yz plane. And you know what that's going to look like. Something like this. Right? Y is always at least 1. And then there's no x specified here, so this is coming out towards us, very much like this. And one on the other side, right? Because of course, for negative values of y as well. and then you're cutting it with this plane. Right, so you have this, and you're cutting it with a plane. So this goes on forever, and the plane goes on forever, so the cut is an infinite cut. And this is really essentially the distance from the origin. Right? I mean, if you had the square root there, that would be the exact distance from the origin. So it's relatively easy to see if we had given it some thought. We did not, but this doesn't have a maximum, but it will have a minimum though, because there is going to be something that is closest. Rick is asking, what if we express a whole function in terms of y only? Both of these? Nothing wrong with that. It's fine. It's going to be the same function, right? So somebody was asking for another example of Lagrange multipliers with two constraints. Do we have anything, or shall I get the book and we can do one? Right, exactly. We said the max was 5. That was incorrect. That was incorrect, and that is thanks to Kai Wen for pointing that out. There is no maximum here, right? What I'm saying is, if you take x to be 1,000,000, and then you can take y to be 999,999, so it's on this plane. And here, you're going to take z to be the square root. You want this squared. So square root of 999,999 squared minus 1. And you're good to go, right? This x, y, and z satisfies both of these. And you see that, I mean, then you can make it as large as you want. Oh, you mean, I see what you mean. You're gonna write this in terms, so here y is, well, probably what you want to do, so I think this is what Rick is suggesting here. You're going to write x in terms of y, so x is 1 plus y. Here you're going to write z squared as y squared minus 1, and you can plug everything into here. So x is 1 plus y all squared, y squared, and z squared is y squared minus 1. There you go. So now you have a function of only one variable. That's very nice. Very nice. And then you want to maximize and minimize that, which is now a function of only one variable. Very nice observation. Very nice observation, and why don't we do it just to see. So this is 6y plus 2. So y is negative 1/3 is the critical point. And for values, for large negative values, it's going to be negative. And for large positive values, it's going to be positive. So we have an absolute minimum occurring at negative 1/3. Did that correspond to the answer we had before? If y is negative 1/3, then x is going to be 2/3, and z 1/9 minus 1, 8/9, plus or minus 2√2/3. Did we have those points? Last time we got 1. When y is negative 1/3, we have 2/3 squared plus 2/9 minus 1. What do we have here? This is 4/9, so that's 6/9 minus 1 is 3/9, so that's minus 1/3. Geez. So Dan is suggesting that we did have that. I'll believe it then. All right, moving on. Thank you. So please make the change to last time's work, right? No maximum. No maximum. Right. All right. Thank you. Well, now something is fishy. Something is very, very fishy. Something's very wrong. What? Something's fishy because, you know, you're not expecting a negative answer here. Oh, sorry. Z. What have I done? There's something wrong, right? There's something wrong because if y is minus 1/3, then this is negative. So this is incorrect. Right, you see what's happening? Yeah, exactly. Z squared is negative 8/9, and then we're in trouble. Yeah, exactly. So how do we fix it? How do we fix this? Y cannot be less than 1. Well, y cannot be between -1 and 1. Right, so here y has to be from -infinity to -1 or 1 to infinity. So this is problematic here, this first derivative chart, right? Because you don't want z squared to be negative. So this restricts the domain for y. So let's draw a first derivative chart again, a better one. Nothing lives in here, decreasing there, increasing there. So really, all you have to do is check when y is plus or minus 1. That's where the minimum can occur. So if y is negative 1, x is negative 1. No. X is 0. And z is 0 as well. And same if y is 1. That's the answer that makes sense. That's the answer that makes sense because we were expecting, right? I mean, you have, do you? Does this make sense? No. If y is 1, x is 2. X is 2. There. So now f of 0 minus 1, 0 is 1, and f of 2, 1, 0 is 5. Were those the answers we had? I think those were the answers we had. There we go. Right. There it is. People were asking what was wrong with setting everything in terms of y. There was nothing wrong. There was nothing wrong with that, but we had forgotten a domain for y. Because if you look at this, since you have z squared is equal to this, right? Or z is plus or minus the square root of y squared minus 1. This implies a domain for y. Y cannot be between negative 1 and 1. So 5 is not the absolute maximum, correct? 5 is not the absolute maximum. And as Gabriel is suggesting, I suspect it's going to be actually a local minimum, not an absolute. How do we get the other value for the derivative? What other value for the derivative? Are you talking about this critical point here? Well, I mean, everything is fine here, except that we had not taken into account the domain. We have the domain for y. It's not all real numbers. So we get a critical point of negative 1/3, but it's not in the domain, right? Negative 1/3 is somewhere here. Well, it could have been a local max. It could have been a local min. We don't know. We don't have enough information here, and it doesn't matter. We know it's not an absolute max because we have understood that this is not a closed, it's not a bounded surface. It's not a bounded intersection, and x, y, and z can actually be as large as we want. Why did I do df dy? Well, we rewrote everything in terms of one variable. So this is really a function of one variable. Right? Somebody had suggested we could have rewritten everything in terms of y, and that's very nice. Midterm grades are going to come out this week. All right. Do we have an example of a Lagrange multipliers question with two variables? Do we want to do one, or are we moving on? The Loy has one. Let's do one from the Loy. Well, I mean, this is just one constraint, right? I think people wanted two constraints. Let me go get the book. We'll, all right. There you have it. So let's be smart here and discuss what we're expecting, if anything. First of all, can we graph this? Right, let's graph it in the XZ plane first. You graph it in the X to Z plane. When Y is 0, Z is absolute value of X. So you know what that looks like. Plus or minus, in fact, right? And in the YZ plane, when X is 0, Z is the absolute value of Y. Again, plus or minus. And then you put everything together with level curves. When z is c, you get x squared plus y squared equals c squared. So these are circles. Right? So you have these cones. Exactly that. This is number 30, page 1027. All right. And then you're cutting it with this, which you recognize as a plane, of course, right? So there it is, right? So some plane with normal 1, 1, 1. Right, and this keeps going forever. And so you're cutting it. All right. What does the function f of x, y, z equal to z mean, right? So this means you have some function w equals z hovering above in a fourth dimension. And we're looking for the maximum value it achieves. And minimum if these exist. So max and min if these exist. And let's think about that. Do we expect a maximum? Do we expect a minimum? Well, let's not worry too much about that for now. And let's just go ahead and do Lagrange multipliers. We'll see what happens. Isn't the cone supposed to be only in the positive z-axis? Well, I mean, you see that if you solve for z, z is plus or minus the square root, right? So you have both of them. If you had just z equals the square, you just have the top, correct? All right, so let's define g to be x squared plus y squared minus z squared, and h to be x plus y plus z minus 24. You actually don't need to necessarily bring the 24 to the other side. I mean, that's going to be up to you. So what do we want? We want the gradient of f to be a lambda gradient of g plus mu gradient of h. In other words, df dx. Well, what is the gradient? Let's work out the gradient. 0, 0, 1. Gradient of g. 2x, 2y minus 2z plus mu gradient of h, 1, 1, 1. Right, so we see that 2 lambda x plus mu is equal to 0. 2 lambda y plus mu is equal to 0. And minus 2 lambda z plus mu is equal to 1. Very well. We can subtract these two to get rid of the mu. And we get 2 lambda x minus 2 lambda y is equal to 0. And if we factor out a 2 lambda, we get x minus y equal to 0. So lambda is equal to 0, or x is equal to y. But if lambda is equal to 0, then from here, this implies that mu is equal to 0. And if both lambda and mu are equal to 0, then the third one implies that 0 is equal to 1, which is impossible. Why 0, 0, 1? Well, it's the gradient of f, right? So partial derivative of f with respect to x, which is 0. Partial derivative of f with respect to y, which is 0. Partial derivative of f with respect to z, which is 1. Right, so you see that if lambda is 0, you quickly get a contradiction. So lambda cannot be 0, so we need x equal to y. I don't really want to erase these. So x is equal to y. Very well. And in that case, we can subtract these two, getting rid of the mu again. And we get 2 lambda x plus 2 lambda z is equal to -1. Right? This one minus that one. And if you factor out a 2 lambda again, you get x plus z. I don't know why I'm doing that. Let's not do that. What do we see here? Let me solve for z. Z is -1 minus 2 lambda x over 2 lambda, and this is fine since lambda cannot be 0. Bottom right is 1 minus x. Where are we? No, contradiction. 0 is equal to 1. Contradiction. I subtracted these two. So we have z is this. All right, so yeah, so we're fine. So z is this. Maybe we want to plug everything into this. X plus y plus z equal to 24, where x and y are the same, and z is this. So we have x plus minus 1 minus 2 lambda x over 2 lambda is equal to 24. Okay, it would have probably been better to rewrite this as minus 1 over 2 lambda minus x. Why don't we do that? So minus 1 over 2 lambda minus x. The x's cancel. And we have x is 24 plus 1 over 2 lambda. And since x is equal to y, this is also y. And z, which is minus 1 over 2 lambda minus x, so minus 1 over 2 lambda minus 24 minus 1 over 2 lambda. So that is minus 1 over lambda minus 24. And plug all of those in to there. We're almost done. Almost done. So that's 24 plus 1 over 2 lambda squared. That's x squared. Plus y squared, which is the same. Can we write two of these? And z, so equal to z squared. Equal to minus 1 over lambda minus 24 all squared. Let's multiply that out. 24 squared, this times 2. That's 24 over lambda and 1 over 4 lambda squared. Is equal to 1 over lambda squared. This times 2, 48 over lambda, and 24 squared. These cancel out nicely. If you bring this to the other side, we get 24 squared. And bring this to the other side, you get 3 over 4 lambda squared. So lambda squared is interchange the lambda and the 24. So 3 over 4 times 24 squared. And so lambda is plus or minus root 3 over 48. All right, that was 768. Is that Joseph? Is that correct? Am I made a mistake? Does that mean that mu can be anything? Probably not. Probably not, but we never bothered solving for mu. What happened on the third to last line? We're here. Did you remember to multiply? Oh, yeah. Is that the right answer for lambda? Does anybody have that? So finally, you can solve for x, y, and z, getting your values. Now the questions, right? So I mean, you're going to get 2 points. So plug lambda in. So x and y are both 24 plus 1 over 2 lambda, right? So when lambda is the positive, you get 2 points here, and your z is minus 1 over lambda minus 24. So you're going to get your 2 points. 1 over 4 lambda squared by 2. I did, in fact, I did. Thank you. Thank you, thank you. Forgot to multiply this by 2. So it becomes minus 1/2. So then it should not be 3 over 4, but just 1 over 2. Thank you. Thank you. So lambda squared should be 1 over 2. And consequently just 1 over 24 root 2. Thank you. All right. So plug those in, get your 2 points. And what? What are we expecting? Were we expecting a maximum? Were we expecting a minimum? If you took a large z, if you fix a large value of z, then what? Then over here, this would be a large negative number. So could you have 2 large negative numbers squaring to give you that large value of z? Or from here, right, since this plane goes off forever and so does this cone, I think it's clear that you can get large values of z. Meaning that this function would not have an absolute max. Seems reasonable. So really all we'd be looking for is an absolute minimum. Which is going to occur at one of those 2 points that you get from here. It does depend on the slopes of the cone and the plane. But right here, the cone and the plane are both infinite. So yeah, it's slightly questionable. But my suggestion is this. Right here, z is the square root of x squared plus y squared. And if you plug it into this, if you interchange these two things, no, let's not interchange. Let's bring this to the other side. You get the square root of x squared plus y squared. And if you square both sides, you get x squared plus y squared is equal to 24 minus x minus y squared. You can square that. This is 24 squared. This times 2. So minus 48 x plus y plus this squared, which is x squared this times 2 plus y squared. Now the x squared and y squares cancel out. Still not immediately clear. I'd forgotten this business, because if you just had that, then by taking x and y inversely proportional, you could have argued it's not an obvious argument. Yeah. Interesting. Well, I suspect that there's going to be an absolute minimum. Right? Because if you have this cone and you're cutting it with the plane, there's going to be a smallest value of z. If this cuts on the bottom, then we're in trouble. Absolutely. So if it cuts through the bottom, then we're in big trouble. All right. Let's not spend any more time on that. Look, I mean, let me say this. It's the process that's important. And getting your values of, well, getting your points is actually what we're after here, right? Normally, it should have been probably clear in the question that you actually had an absolute max and an absolute min. Well, I mean, that actually depends on the slope of this cone. If they have the same slopes, they might never cut. Yeah, but I think what do I think? Why don't we look at the tangent plane? If we look at the tangent plane to the lower cone, so the normal to the tangent plane at some point in 1 or this, if you multiply the whole thing by square root of xy, and that is just this. So this is xy minus z. So at any point x, y, z, the tangent plane is going to be pointing in the direction of x, y minus z. So this is going to be the normal to that plane. Depending on what x, y, and z actually are, yeah, all right. Let me give this some thought. Tonight to see really what's going on. But I mean, a priori, without having done any work, I would have expected, here's what I would have expected. I would have expected a minimum, no maximum. Well, we're trying to argue if we have an absolute max and or an absolute min. Right? The question actually doesn't even say. The question suggests that there's both an absolute max and an absolute min, but we're wondering if that's even true. Right? Because the one we did in class last week did not. All right. We've probably spent too much time. We could have a max. We could have a minimum without having a maximum. What I expect is happening is that this plane is cutting the top part of the cone and not the bottom. And what I expect to happen is that you're going to have the smallest z value, but not a largest. Right? What I expect to happen is that the cut is going to look something like this. Where this keeps going on forever. There probably is. That's what I was trying to do here. If you can show that there are large values of z occurring without bound, then you'd be good. Does that happen easily? If you take a large x and an equally but negative large z, large y, yeah, no, you see that doesn't matter. That doesn't work. All right, look. Enough time wasted on this. I'll try it tonight, and I'll let you know. All right. When I wanted to tie up this loose end that the book doesn't discuss, Taylor series in higher dimensions. All right, let's recall that if you have a function, we were hoping to write it as an infinite sum. And you remember how this was done? Well, I mean, we did it not too long ago, right? Right, we did this not too long ago. And you remember that, right, a0 has to be the function at 0, at a. A1 has to be the derivative at a over 1 factorial and so on, right? You remember how we did this by taking the derivative and so on. This idea extends. You can extend to higher dimensions. Let's do it in 2 variables, but you can do it in more variables as well. I suppose you wanted to have some sort of polynomial in x and y, right? So a1 x minus a, but you also want y's. Let's call it b1 y minus b. And then a second derivative, if you will. a2 x minus a squared, b2 y minus b squared. But in your work with partial derivatives, you know the mixed partials come into play as well. So maybe we want an x minus a, y minus b. And so on and so on. This is not in the book, that's right. Most books discuss Taylor series in higher in more variables. For some reason, our book does not. So, you know, I mean, I'm just mentioning it in passing. And you can work out, right? I mean, you see that if you plug in x equals a and y equals b, everything cancels except the first term. So f of ab is a0. And then if you differentiate with respect to x, you see what happens. This disappears. Here we get a1. That's gone. This is 2a2 x minus a. This is gone. This is a3 y minus b. And so on and so on. And if you plug in the point ab, that's gone. That's gone. Everything is gone except a1. Everything is gone except what should remain. And so on and so on, right? When you, if instead you did fy, right, that's gone, that's gone. You have a b1, this is gone. This is 2b2, y minus b. This y minus b is gone, a3 x minus a, and so on. And when you plug in the point AB, this is gone, and you're left with just a b1. And let me point out, you know, second derivative works as it should. And of course here, if you're differentiating with respect to x and then y, or y and then x, it's going to be the same thing. So the point is that it's understood that you have equality of the mixed partials. So for this Taylor series business to work, you need equality of the mixed partials. So you need your function to be well behaved, and so on, exactly, at least to satisfy Clairaut's theorem. Why is there no B0? Well, you can call it B0, it doesn't matter. Right, you can call this B0 if you want. The point is that you can solve easily for all the coefficients. That's all it is. So it's really just, well, fine if you want to there as well, calling A0 and B0 the same thing. You know, it's just notation at this point. All I'm saying is these are the coefficients respectively, and you can solve for them in the usual way. Again, people, don't focus on what I'm calling the coefficients. It doesn't matter. Call them whatever you want to call them. I don't think this is going to be testable material. Again, we'll have to wait and see what the other instructors say about that, but we can't find A3, why not? If you look at this and you differentiate this with respect to y, this is 0, this is 0, there's no y there. This is A3. And then you'll get other stuff which has an x minus a or a y minus b. Right? Or if you differentiated this one with respect to x, you would also get A3 plus some other thing. So you see the underlying assumption is that f of xy at AB should be the same as f of yx. In other words, you should have equality of the mixed partials at every single point. People, don't get lost in the notation, call it whatever you want. All we're doing here is solving for the coefficients. Give them a name and solve for them. It doesn't matter what you call them. In the end, if you put everything together, what are we saying? We're saying that A0, which is f of AB, plus A1, fx of AB times x minus a, plus fy of AB times y minus b. What else have we found? We found A3 without actually finding A2 and B2, but you know that it's going to be fxx at AB over 2 factorial x minus a squared, and fyy at AB over 2 factorial y minus b squared, and then A3, which is f of xy at AB, x minus a, y minus b, and other stuff. And finally, let me just point out that the first 3 terms of your Taylor series is the linear approximation, right? Or tangent plane approximation. How are we doing here? What do you mean by that, Lloyd? You mean using up to degree 2 to approximate? We do not, right? Because the underlying assumption is that fxy is the same as fyx. And in the differentiation, no 2 arose. When you say higher order, Lloyd, you mean with more variables or the order of the polynomial? Then yes. Yeah, I mean, there's no reason for you to stop at the tangent plane, right? You could have, you know, in the same way that you have Taylor polynomials in one variable, Tn, approximating your function, the same is true here. B3, I don't know that B3 is equal to A3. Did we even define a B3? What was the B3? Look, all I'm saying is, naturally, I'm suggesting, Adamar, you don't need an fxy versus an fyx. They both turn out to be the coefficient A3, the coefficient of x minus a times y minus b. Let me quickly take a few moments to discuss our next topic, which we should have done today, but we didn't. So this is another, as Gabrielle points out, this is another justification, if you will, for the tangent plane approximation, right? It's the first 3 terms of the Taylor series. Exactly that. So if you remember from last semester, given a function of one variable, we were looking for the area underneath the graph. This is assuming your function is positive, of course. And how did we do that? We started by approximating the area under the graph by partitioning your interval into a few pieces. And on each subinterval, we took a point and looked at the rectangle with that height, and you repeat that throughout the interval, and you add all of these areas up, and you get an approximation to the area under the graph. This is known as a Riemann sum. right? Which is the sum of all of these rectangles. The sum of the areas of these rectangles. The areas f of xi star delta xi, right? So the width times the height, and you add all of these up. And if, as n goes to infinity, as the partition gets finer and finer, if this limit exists, regardless of what the xi star are, if this limit exists and is always equal, then we say the function is Riemann integrable. And that limit is equal to the integral. We're going to do exactly the same in higher dimensions. Geometrically, you've got some domain, and you've got some function hovering above. And we're going to ask the question, if you restrict your function to this domain, what is the volume underneath the function restricted to the domain? Well, who knows? But we can do the same thing. We can approximate. If you partition this domain into some rectangles of length delta xi and width delta yj, and take a point xi star yi star, xi star yj star, look at its image, and consider the box of height f of xi star yj star, length and width, these, right? So the volume of this box is f of xi star yj star delta xi delta yj. That's the volume of one box. And you're going to add all of these boxes over I and j. Or, if you prefer, maybe a double sum over I and j. And if the limit, as you have more and more boxes, as these boxes are getting smaller and smaller, these rectangles here, as these rectangles are getting smaller and smaller, if the limit always exists, regardless of which points you take, then we're going to say that the function is Riemann integrable, and we're going to denote this limit by the double integral over the domain D. Now, we don't have time to consider some examples today. We'll do that on Thursday. But you'll see that the point is not to learn how to integrate again. You know exactly how to integrate. The important thing here is going to be the setup of the actual integral. So integration is not any more difficult. It's exactly the same because of partial differentiation. Partial differentiation, when you differentiate with respect to x, you treat the other variables as constant. So here in integration, the opposite of differentiation, the same is true. When you integrate with respect to x, you treat all the other variables as constant. So it's just as easy. It's going to be the setup of the integrals that's important. And we'll see exactly what I mean by that on Thursday. Thank you all for coming. I'm going to work out that Lagrange multipliers question. See if I cannot give you a nice, simple explanation as to what's going on. And we'll pick this up again on Thursday. Thank you all for coming. I will see you then. I've posted a new web work, so please have a look at that. Taylor series have absolutely nothing to do with this. I thought it was important that we take a minute to discuss it, especially since it's not in the book. All right, so know that it's out there, that other books do discuss it, but ours does not. Other than the new one, there might be one last one. Well, there will be one last one. Wait, there will be at least one. There'll be two more. Let's say this. Two more web work to come. One that I'll probably open up on Thursday, and then one afterwards. All right. See you guys on Thursday.